Hello, I'm going to talk to you about antimatter. That was off to a good start. I'm not gonna, start the video again because it's important that you get to see the whole process. Right. Okay. So we should be already familiar with the idea that Einstein came up with E equals mc squared. Enough people bang on about it. Energy is the E. M for mass, and c squared corresponds to the speed of light squared. Now, British physicist Paul Dirac said, in terms of the energy that's locked up in particles, there should be some corresponding antimatter for every version of matter. And he said this in 1928. And in 1932, four years later, we discovered the positron. So Paul Dirac, that British physicist, found it to be correct. So let's have a look at matter. Let's have a look at the antimatter equivalence. This is very real. Positron emission tomography is used in medicine, also known as PET scans. So this is not just theoretical physics. It's got actual practical applications. So let's take the particles known as the electron, the proton, the neutron, and I'll introduce you to the neutrino as well. Neutrinos are elusive particles. We don't know a lot about them. We're saying that they've got zero rest mass, zero charge, and zero rest energy. Okay, neutrinos will come in handy when we talk about the weak nuclear force. Okay, so any data sheet will tell you that the electron's rest mass is 9.11 times 10 to the minus 31, and it will tell you that your proton and neutron rest masses are 1.67 times 10 to the minus 27, where we're only going to 2 decimal places. And remember, I'm leaving the neutrino blank because we're saying it's got zero rest mass. Okay, neutrons do not have charge, but electrons do. Electrons carry negative charge. Protons carry positive charge of 1.6 times 10 to the minus 19. Neutrinos, again, we're saying is zero at this stage, so it has no charge. Okay, so in terms of the rest energy of the particles, these are stationary particles. How much energy is locked up within an electron? It's 0.511 mega electron volts, where a mega electron volt is the equivalent of 1.6 times 10 to the minus 13 joules. Okay, for a proton, it's 939.257, and for a neutron, it's 939.551. So there you can see that the neutron and the proton have got different rest masses and rest energies rather, and that is down to a discrepancy in the rest mass. Neutrino again will say zero. Right, okay, so for the equivalence of antimatter, a positron, an antiproton, an antineutron, an antineutrino. And we'll talk about what happens when these interact later. Okay, in terms of the antimatter equivalence, a positron will have exactly the same rest mass, but it will have the opposite charge. So it'll be 1.6 times 10 to the minus 19, but it will be positive. An antiproton will have the same rest mass as a proton, 27, do excuse my handwriting, and again it will have a negative charge of 1.6 times 10 to the minus 19. A neutron will have the same mass and it'll have the same charge. Difference is between neutrons and antineutrons are down to their quark composition, and we'll talk about quarks and leptons in the future. Antineutrino, zero charge, zero rest energy, and the rest energies for these stay the same. So when they are stationary, their locks up energy are the same value as the matter equivalence. Right, okay, so I'm just going to rub this bit out at the bottom, and I'm going to talk about the practical implications of this. Right, okay, now matter and antimatter are produced in pairs, and we call this pair production. And what happens is we have a photon of energy, and what happens from that point is, if it's got sufficient energy, then it will produce matter and it will produce antimatter. So there I've done an electron and a positron as an example. Okay, now some of you are wondering where you get the mass from here. When you do further particle physics, if you're going to do it at degree level, then what you've got is you've got a nearby nucleus that recoils over here to satisfy conservation of momentum, but you don't need to concern yourself with that. So we know that the positron rest energy is 0.511 mega electron volts, and this is 5.11 mega electron volts. This means that our photon must be at least 1.022 mega electron volts, because it needs that much energy to produce the two particles. Okay, the reason why it's greater than is because it will have kinetic energy as well. Okay, so to satisfy this criteria, it's got to be greater than this value. Okay, these will also have kinetic energy. They don't just spring into life and stay still. Okay, so these are their rest energy values. So what we're saying is we need 2 lots of HF to make 2 lots of particles with energy. So therefore, here, if you add them together, HF is equal to E. Right, okay. Now, positrons do not survive for very long on their own in the atmosphere. What happens is a positron will usually meet another electron. They will collide, and release energy. So this mutual destruction is why you don't get positrons. Positron usually meets an electron, and that causes the annihilation process. So we have got 0.511, 0.511, and your 2 photons produced will also be 0.511, 0.51 electron volts. Be careful if you have to do any calculations with these. Remember that 1.6 times 10 to the minus 19 joules is equal to 1 electron volt, and 1.6 times 10 to the minus 13 joules is equal to 1 mega electron volts. Okay, so don't forget you need 2 lots of that HF. I'm going to get rid of that 2. I'll tell you why I'll get rid of that 2, because that corresponds to 1 photon value. So 1 lot makes 2 lots of energy. I think that would be a slip to put the 2, to be honest with you. All you have to appreciate is this is double that value over there. What I would do if I were you is I'd have a look at the typical exam questions you get with this. Make sure you do plenty of practice with converting your rest energies into pair production and annihilation. Thank you very much for watching ATB.